Stripping down science. The Naked Scientists.
Hello, it's January the 16th, 2011, and this is the first Naked Scientists question and answer show of the year, and it's also my birthday, which is very nice. I'm Chris Smith, and with me is Dave Ansell. Hello, Dave.
Hello.
And I'm Sarah Coster-Perry.
And coming up, the answers to all of your science questions, including what happens to a fizzy drink in space, why does a knock on the head make someone see stars, and do surgical implants attract lightning? Sarah.
We'll also be hearing about a new system to keep the drummer in control.
It's something that I can interact with. So it's a computer, it responds to me like another musician. I interact with it as I do with the bassist and the keyboardist and the singer. In a live situation, if the audience is enjoying it and there's a buzz going on, I can go there, I can speed up, and I know the machine's there. I go for it, it listens, and away we go, you know.
And I've got an experiment to reveal how rockets work and why planes can't be powered by vacuum cleaners. You need a couple of bendy straws and a pair of scissors and a lungful of air.
I'm quite glad that planes can't be powered by straws and vacuum cleaners. That could be quite a long suck, I think you could say. Thank you, Dave. If you'd like to get in touch with us, meanwhile, then you can contact us through Twitter. You tweet at Naked Scientists. You can also write on our Facebook page. That's thenakedscientist.com/Facebook. It'll take you there. Or you can drop us an email. The email address is chris@thenakedscientist.com.
The Naked Scientists podcast is powered by UK Fast, the UK's best hosting provider. On the web at ukfast.co.uk.
Well, this is The Naked Scientists with Chris Smith, Dave Ansell and Sarah Coster-Perry. And first off, let's take a look at some of this week's top science news stories. Dave, what have you got there?
Well, a quicker, cheaper way of making computer chips has been developed. Now, integrated circuits or silicon chips are now absolutely critical for every part of everyday life. And they're so cheap that it can actually make sense to put a computer inside a juggling ball. They're only cheap if they're made by the million, so most of the problems solved with them have to be done with general-purpose processors. These are great, but they can be hundreds of times slower and less power efficient than a custom-designed circuit, because they've got huge amounts of circuitry there which just isn't being used most of the time. You make a silicon chip by making a mask with a pattern on it, then you shine UV light through it, photographically transferring this pattern onto a layer of plastic over the silicon, then etching away some of the silicon where the plastic has been removed. Different materials are added onto the silicon and etched away up to about 30 times, and you end up with a working computer chip. The problem is that these masks are incredibly expensive. A set of them can cost up to $3 million, which means if you only want a few hundred or a few thousand of a specific kind of chip, each chip is going to cost an absolute fortune. And also, if you make a mistake making this mask, it's an immense amount of money wasted. So it's very, very difficult for development. One alternative to this process that's been existed for a while is to get rid of the mask completely and use an electron beam to write directly onto the plastic. This is very, very slow because there can be over 1 billion transistors on a modern chip. Now, engineers working for KLA-10 Core have developed a system which, instead of using one beam, uses 1 million at once. They send a big wide beam of electrons at a special chip covered in special pixels, which can be programmed to be the transparent to the electrons or act as a mirror. And then they focus these reflected electron beams back onto the plastic over the silicon. They can then move this beam around and write onto the chip over 100 times faster than the previous method.
But in the method you described first, you said they use ultraviolet, but now they're beaming electrons back on. So how does the electron actually write the signal into the chip?
Well, essentially what it's writing onto is this layer of plastic. It's you dump a load of energy into this plastic, it alters the plastic chemically, and then it doesn't wash off. So then you have a pattern on the chip, you then etch away the bits which aren't covered in plastic, and you end up with a pattern inside the chip. This is unlikely to compete with photolithography for large quantity production, but for research and specialist applications like the military, it could be very economic.
So in other words, if you wanted to make a small number of very specialised chips, you could do that at much lower cost using this particular technique.
Yeah, more expensive than in huge bulk, but still far, far cheaper than at present.
Dave, thank you very much. Well, also, for sufferers of a heart condition that runs in families and can cause sudden cardiac death, especially amongst young people, there's a new technique to develop and explore new treatments and to explore the disease in detail. Now, the condition I'm referring to is called long QT syndrome, or LQTS. It's quite rare, but it does afflict young people because it's a genetic condition that causes the heart muscle, and specifically cardiomyocytes, the cells that make up the heart muscle, not to reset themselves electrically after they beat. Because when a heart cell beats, it gets electrically excited by letting some sodium come into the cell, and it then resets itself by putting potassium back out of the cell. And in people who have this long QT syndrome, the cells don't reset themselves quickly enough, and this can result in the heart going into abnormal rhythms, and sometimes those rhythms can be sufficiently abnormal to trigger cardiac fibrillation, or in some cases cardiac arrest, and so people can just have sudden death. And if it's identified early enough, then it can be managed with drugs. But actually studying it in the first place and working out which drugs are good and which are bad, and when you build a new agent, finding out whether it can impact on the disease is very difficult, because it's very hard to model a condition in a cell, in a dish, if you don't have a cell to work with. But now researchers in Israel have come up with a possible solution. There's a paper by Ilanit Itzaki from the Institute of Technology in Israel that's literally just come out at 6 o'clock Sunday in Nature. What they have done is to take a lady who's got one form of long QT syndrome, take some skin cells called fibroblasts from this lady, they put them in the culture dish and then expose them to a virus which adds to those cells 3 special genes called SOX2, KLF4 and OCT4. And the action of those genes is to make those skin cells unspecialise and go back to becoming very primitive stem cells. So they become what are called iPSCs, or induced pluripotential stem cells. And if you culture those cells in a special culture dish, then they turn into what are called embryoid bodies. And in other words, they start to produce all of the tissues you would begin to see in a very early embryo, including heart cells, because when the researchers watched this happening down the microscope, they saw that some of the cells that were developing were beginning to beat autonomously, just like embryonic heart cells. And by identifying and isolating those cells and then studying them, what they found is that the cells display all of the electrical abnormalities that adult heart muscle cells do. They also respond chemically to drugs in exactly the same way as mature heart cells. And so they were able to test various agents, some of which we know work very well in long QT syndrome, and also some new agents that are being tested and explored for their potential to treat this condition as well. And as they say in their paper, the concept described may also be extended to model several other human genetic disorders, enabling translational research into disease mechanisms and therapies. In other words, this is a very clever stem cell technique to produce cells that directly mimic the condition that an adult has, so that in the dish you can explore, without having to make animal models or anything, the very cells that are affected by a disease, and then explore whether or not there are drugs around or drugs that you're making actually work to combat that condition.
That's an incredible piece of research, because, I mean, obviously your heart is such an essential part going on there, but obviously there are issues with using animal models for this sort of thing. So with the improvements in stem cells, you know, it's a really exciting area of research.
Well, the major benefit is that rats don't get long QT syndrome. And if you put the gene that we know goes wrong in the human into the rat, you don't know to what extent the differences you're seeing are just because that gene is abnormal or because it's interacting abnormally with other genes that it wouldn't normally be in a cell with. So by having the cell that's a human cell from the patient with the condition, you can then test how that person would respond to any drug you intend to use or an experimental agent before you've even gone near a person. You just have to do it all in a test tube, which is, as you say, incredibly powerful.
Well, moving on from hearts to food now, the problem of how we might feed the Earth's growing population in the future has come under further scrutiny this week with the publication of Agrimonde, which is a book that is the summation of 2 years of work by 2 French institutions, INRA, the French National Institute of Agricultural Research, and CIRAD, which carries out agricultural research to help developing countries. Now, despite the study being carried out by 2 French institutions, the book has actually been published in English in order for the results to be more accessible on the world stage, because the institutions thought it was important for the world to know what they'd found. I travelled to Paris for the launch of the study, and I spoke to Patrick Caron from the Institute CIRAD about how even today we struggle to feed everyone on Earth.
There is actually a very big problem. Of course, we are used to find food in the supermarket, and most of us used to have money in our pocket to buy this food, but that's not the case. in all countries, and that's not even the case in our own countries sometimes. We have to remember that 1 billion people in the world are suffering from what is just unacceptable. One death from malnutrition is one death which should not be accepted for ethic reasons. The human history was paved with this problem, and starvation has been part of our history. But in the 70s, we discovered a tremendous growth in human population at the world level.
And it's the continued increase of this population growth, predicted to reach 9 billion people by 2050, that's causing concern. Now, concern about feeding the growing population isn't new, but this is the first study to integrate looking at patterns of food production and consumption over the past 40 years, with two possible scenarios for how we might proceed with providing the world with food in the future. The first scenario they called Agrimonde 1. In this scenario, the world is characterised by sustainability, so a decrease in both undernourishment and overconsumption, ecological intensification of farming and security of trade. The second scenario, called Agrimonde GO, is the kind of business-as-usual scenario where food production increases year on year as it has done in the last 40 years, trade is liberal and little thought is given to environmental impact of feeding the world. Agrimonde 1 would involve a lot of changes, not just with agriculture, but also our eating habits. The current world average daily calorie consumption is 3,000 kilocalories, but this is not evenly distributed. In some areas, people eat a lot more, like in Europe and the United States, and in some areas, people eat a lot less. The aim for the scenario Agrimonde 1 is to have everyone eating 3,000 kilocalories a day, irrespective of where they live. And the way people consume and waste food is an area that Agrimonde actually looked at in quite specific detail, and it's an area which will need to see a lot of changes, as Marion Guyot from the French National Institute for Agricultural Research explains.
So the eating habits are very different in different parts of the world. Our European eating habits, for instance, of course it's not sustainable because first you have health questions, and then it's not sustainable if all the world begin to eat as we do, because then you have a pressure on production that will be tremendous. So what we did is we looked at a scheme of eating habits that is, of course, compatible with good health of all the people, that is to say 3,000 kilocalories. And then we looked at the fact, is it possible to feed the world with that kind of eating habits all around the world? And the question is yes, with some questions we have to work on.
And given that the institutions INRA and CIRAD that carried out the study both carry out agronomic and agricultural research, this is one of the ways we could really innovate in the future. Genetic techniques could be used to increase yields, either by genetic modification to produce pest-resistant or salt-tolerant varieties of wheat or corn, or by marker-assisted selection, which is a way of making the old-fashioned method of plant crossing to produce new varieties with the characteristics you want. It makes it much more efficient. But producing these new varieties will not be the whole story. François Houillet from the National Institute of Agricultural Research.
I think if we consider the agricultural challenges that we face and we think to the different solutions that we may imagine, we need to consider the way we grow the crops. And by the way we grow the crops, of course, I think to nitrogen and the different fertilizers that we use. I think also to the pesticides that we have to reduce. We also have to think to the rotation of the crops. We will need to combine different approaches, different disciplines, different techniques.
So we need to adopt an integrated approach to increasing food production, and we need to change our eating habits and stop wasting so much food. Not exactly an easy fix, but if we can manage these things, then the conclusion of the book was that, yes, we will be able to feed the world. And if you want to read a summary of the report, you can visit our website, thenakedscientist.com/news, and follow the links.
Sarah, thank you very much. Dave, let's move on to an exciting new form of metal, and not music either.
Indeed. A stronger metal alloy has been developed than ever before. Metals are wonderful materials. They've revolutionised human life for thousands of years. Their structure is all crystalline, which means that atoms are arranged in repeating patterns over a relatively large scale. They're not nearly as strong or stiff as you'd expect from the bonds between the atoms. One of the reasons for this is that tiny defects in the crystals can move through the crystal relatively easily, allowing the crystal to deform at much lower forces than you'd expect otherwise.
So that's why metals are sort of ductile. You can pull out a metal into a wire, for example.
Yeah, especially things like copper are very, very ductile, and you can hit them with a hammer and they bend rather than break. One way of making the metal stronger and harder is to change the metal structure to be more like that of glass, with no large-scale repeating structure. You do it by taking some molten metal when the atoms are arranged pretty randomly, then you cool it very, very, very quickly. And especially if you've got a fairly complicated alloy with lots of different sized atoms, they won't crystallise and form a glass-like structure of metallic glass. These are very, very hard and wear-resistant and very efficiently elastic, so sometimes they're used for golf clubs. But they're not especially tough. This means they can't absorb a lot of metal because they can't, a lot of energy, so they can't deform, so they tend to crack and shatter, a bit like a conventional glass. Marius D. Dementru and colleagues from the California Institute of Technology have managed to greatly increase their toughness by making a metallic glass from a palladium alloy, which has made the alloy much better at deforming slightly under very, very large shear forces.
So what does the addition of that palladium do to the metal to make it like that?
It just means that they can rearrange their bonds slightly more easily. They can slide over each other slightly more easily than they would do otherwise, which means if you've got a crack going into the material, instead of the crack carrying on growing, what happens is it kind of gets wider and flatter, and it stops being so sharp, all the forces drop, and everything stabilises.
So what could you do with these sorts of metallic glasses? Why do we think they're helpful?
Well, this one would have a better combination of strength and toughness than any other material produced. So if you can make it on a huge scale, it would be a wonderful thing to build buildings out of, build chips out of, whatever. There is, however, a minor problem. Palladium is much, much rarer than gold and costs about $16,000 per kilogram. So it's unlikely to be used for anything very large soon, but the group's working on possibly slightly cheaper alloys with similar properties in the future.
Prove the point, in other words, and this is a way of saying you can do this. Now we need to find something that will do the same job as the palladium but is more abundant, so it doesn't cost as much.
Yeah, totally.
Thank you, Dave. Now, traditionally, the drummer in a band is there to set and to maintain the pace of the music. But if pre-recorded samples and backing tracks are included in a performance, instead, the drummer now needs to try and keep up with them. But now, a new computer programme which has been developed by musician and researcher Dr. Andrew Robertson at Queen Mary University of London could hand control back to the drummer. And to tell us more, here is Jane Reck from the EPSRC.
Like a lot of bands, Dr. Andrew Robertson's group uses a mix of live performance with pre-recorded backing tracks and synthesizers. But Andrew's band is different because he's made it possible for the drummer to set the pace of the music. If the drummer wants things to speed up or slow down, everything else follows the pace they set.
I designed a drum tracking system that's called Beekeeper to take in microphone input from the drums and to control sequencers in terms of their tempo to stay in time, even though there are slight fluctuations in tempo. One analogy is, if you're on a motorbike, you're on a motorway and you're trying to catch up with a car, and that's ahead of you. What you have to do on the motorbike is accelerate. Then as you're approaching the car, you need to actually go off a bit and sort of slightly slow down from the speed you are so that you're at exactly the same speed as the car and you're at the same side of the car. You're looking, you look to your right, there's the driver's seat. So you're trying to be at the same speed and actually at the right place as well. So there's no point being at the right speed and being half a beat ahead of the car. I see the drummer as the car. He's kind of just cruising along. And the system is effectively more of the motorbike because it actually has the ability to zoom up and catch up or put on the brake and slow down slightly. So I've made that system for music.
Andrew is a researcher at Queen Mary, University of London. He says it's the first software of its type for drummers. The drums are linked up to the computer software by microphones.
We just pop a mic in the kick and one in the snare, put it out to this computer. This is analysed for something called onset detection. So when they hit that drum, you get an event, and it's sent to you as a bang or it's a hit. So it's analysing a sequence of events. This is done relative to a click track. that the sequencer's using. The computer uses its metronome, it's got its own idea of bars and beats of what it's doing. So you send out, on the one hand, the computer's click, on the other, the kick and the snare from the drummer. The software is making the best adjustment to align the two. So the best adjustment in tempo, so you're at the same speed and the same exact place as the drummer. It's also got a nice count-in where you can count in with the sticks, and that initializes it, ready to go.
This is the drummer playing live with backing from a synthesised bass line. As the music progresses, a robotic xylophone is also brought in. The software controls the speed of the bass line and the xylophone to keep up with the drummer. You'll hear different parts from this track, so that by the end of the piece, when the drummer has gradually built up to a much quicker speed, you'll be able to hear a real difference in the tempo, with everything following the lead of the drummer. So the music goes from this to this. And finally to this. Drummer David Knock says the software makes a big difference to a performance.
It's something that I can interact with. So it's a computer, it responds to me like another musician. I interact with it as I do with the bassist and the keyboardist and the singer. In a live situation, if the audience is enjoying it and I'm enjoying myself and there's a buzz going on, I can go there, I can speed up. I might find that this chorus, I really want to kind of give it a bit of extra energy, and I know the machine's there. I go for it, it listens, and away we go, you know.
Andrew's work is funded by the Engineering and Physical Sciences Research Council and the Royal Academy of Engineering. So it's UK-funded research that's helping to keep this country ahead of the game in the music industry. Nowadays, a lot of musicians make more money from live performances than music sales. So Andrew says it's vital that these musicians are able to offer more spontaneity in their performances to keep people coming back for more.
It's very difficult for musicians to actually sell hard copies of their records, so they don't see the kind of revenue they used to see when they had the vinyl and CD sales. Actually, it's in the live arena that a lot of things are happening. Given that, when you look at the bands out there that are exciting, a lot of them are using technology. They're bringing technology into the shows. If bands take this up and start using it, I think they benefit from it.
You can find out more about the software at b-keeper.org, and Andrew's band is called Higamos Hogamos.
What a fantastic invention. That was Jane Reck from the EPSRC, and she was talking to Dr. Andrew Roberts from Queen Mary, University of London. And if you'd like to catch up on anything we've covered so far this week, the references and the transcripts for each of the news stories we've discussed are online at thenakedscientist.com/news.
Laying the facts bare. The Naked Scientists. For more information, look us up online at nakedscientists.com.
And you're listening to The Naked Scientists with Chris Smith, with Dave Ansell and with Sarah Coster-Perry. Right, let's kick off with Alan. Hello, Alan.
Oh, hi.
Go for it.
Yeah, the question is, I was looking at my road tax renewal form, and I see that I'm taxed on how much CO2 per kilometre my car emits. Now, my car emits 218 grams of CO2 per kilometre, and my car averages, say, around at 51.5 kilometres to the gallon, which equates to about 11,227 grams per gallon. Now, a gallon of petrol weighs only 3,300 grams, so where does that extra mass come from?
OK, well, that's a really interesting question, Alan, and I'm very glad that you raised it. So the best way of approaching this is to think about the chemistry that's going on. So what's the chemical formula of the reaction in your engine between the fuel and the air? Well, the fuel is a hydrocarbon, and that means it's long chains of carbon atoms all glued together. And to make things simple, we'll assume that each carbon atom is associated with 2 hydrogen atoms, because that's what a hydrocarbon chain looks like. So CH2, the hydrocarbon, plus oxygen, O2, and we're going to need 2 molecules of oxygen, is going to make a molecule of CO2 and a water molecule, because the product of combustion is carbon dioxide and water. Now, if we look at how much a molecule of the hydrocarbon weighs, for each CH2, that's 12 grams of carbon, and H2 weighs 2. So we'll say that it's 14 grams for each mole or each group of molecules for the hydrocarbon. And the CO2 weighs 44. So therefore, the proportion of the product's CO2, that is the hydrocarbon to start with, is 14 over 44. So if we ask Dave, who's got his calculator ready, Dave, what is 14 divided by 44, please?
It's just below a third.
In other words, what comes out of the exhaust pipe is about 3 times the mass of the equivalent fuel that it took to make that in the first place. So, if we now go back to your original figures, where you say that the gallon of the fuel weighs about 3,300 grams, and that actually after you've done a gallon's worth of mileage, you reckon you've produced 11,227 grams, what's the reason for the disparity? Well, if we times the about 3 times 3,300, if you could just do this, Dave. So what does that come to?
Comes out as about 10,400 grams.
OK, so therefore we're almost in the right ballpark for the 11,000-ish that you quote in your car's figures. So actually the reason for the disparity is that you forgot to take into account that oxygen weighs something, and therefore CO2 is actually a lot heavier than the original carbon that went in to make the fuel work in the first place.
What's coming out of the exhaust is not all that harmful then, apart from the CO2.
Well, you say apart from the CO2, but that's the bulk of what comes out, unfortunately. And if you look at the planet as a whole, burning fossil fuels has contributed an enormous amount. We put out something like 40 billion tonnes of carbon dioxide into the atmosphere every year. That's about 12 billion tonnes of raw carbon going into the atmosphere. And this is fossil carbon that was locked away millions of years ago and turned into oil and coal. And as a result, you're net contributing to the CO2 in the atmosphere, which we think is linked to a rise in atmospheric temperatures because of greenhouse effect, and this will warm up the planet over time. The levels in the last 200 years have gone up by 30%, so that's not bad for a single species to have altered the composition of the atmosphere of a whole planet by 30% for one gas in 200 years. It's pretty good going, actually, in terms of an achievement for mankind. Not necessarily a good one.
Because this carbon's bound up with twice as much oxygen, that's why it's causing the bulk. So it's just...
That's right.
Yeah.
Absolutely right.
So it's not just carbon, yeah.
Thank you, Alan.
Okay,
good to have you on the show.
Very interesting, thank you.
If you'd like to join us on The Naked Scientist, tweet your questions to @NakedScientist or write them on our Facebook page. That's at nakedscientist.com/Facebook, and it will take you there. You can also email, of course, chris@thenakedscientist.com. Sarah, I have one here for you, if I just drag it out. Joyce is wondering, will the salt that we put on the roads to stop frost hurt the wildlife?
Well, of course, because we had to put rather a lot of salt and grit out on the roads with our sort of rather glacial winter this year. Well, it's kind of a difficult question to answer because, well, obviously, when the snow melts, it'll dissolve the salt and the salt will get washed away. So if it gets washed into something like a lake or a river, it can build up. And if you imagine what that's going to do to the wildlife in the river, it's a bit like dropping a freshwater fish into seawater, and they're not adapted to live in salt water, so that could cause some serious issues. In terms of the animals that might happen upon the salt when it's on the road, obviously, I don't know if you ever had to put salt out to stop slugs eating your lettuces or any of your things in your garden, Chris?
I use beer, actually.
Yes, I've heard that that's supposed to work quite well. Well, if you put salt on a slug or a snail, they sort of go all frothy, and it's a bit of a cruel way to kill them. But so they'll obviously have problems. But with large animals like foxes and rabbits, although eating a lot of salt could make them quite sick, it's unlikely that they'd be able to ingest that much. A couple of studies, actually, that came out in the last couple of years, one from the University of Minnesota and one from the University of Toronto Scarborough, found that salt from roads in those local areas had actually contaminated local water supplies. And the Toronto study also showed that wildlife had been affected because they saw a decrease in fish in local creeks and a decrease in aquatic species diversity. But there is a key point here that our roads are designed to drain into drains. So when the snow melts, if it's on the roads, it will drain into drainage and go to a water treatment plant. So in theory, it shouldn't cause too much problems unless you use a lot of it and then it gets washed into standing water. So it could cause problems, but no one's quite sure. Or
back into the sea, of course, because many of those storm drains go into the sea at the coast, don't they? So that's quite handy because the salt just goes back to where it came from in the first place, really. Well, yes, I suppose. And also, it's still the most cost-effective way of dealing with ice and snow. And, people have still got to get to work and drive to school, so... There's always going to be a cost, whether it's a human one or a wildlife one, isn't it? Dave, Matt in Milton Keynes, I love this one. He says, do surgical implants attract lightning? My friend had a huge operation to correct double scoliosis, and I've spent considerable time helping her to recover. The operation involved fusing a titanium rod to her spine to replace, but not remove, an old surgical steel one. I have nicknamed her Lightning Rod because she's now petrified to go out in the lightning. 2 questions. First, is she more likely to attract a lightning strike? And secondly, could the metals in some way also have an effect on radio signals? At the time, she appears to affect radios and mobile phones just by being in close proximity to them.
I think the answer is yes, but only a very, very little bit. Okay, lightning, if the clouds get very, very highly charged, this charge will attempt to flow down to ground. The problem is air is an insulator, so it's got to flow through something. The way you can get electricity to flow through air, if the voltage gets big enough, the electric field gets big enough, you can rip electrons off the air. They can then fly through the air and bash other electrons off, and you get a big conducting path, which electricity can flow down. It's a bit like a wire, and the lightning bolt can go down through this path. Air gets very hot, you get thunder and lightning. The shorter this path has to be, and the better the conductivity route up before the lightning has to start, the easier it is for the lightning to form. So if you the lightning will tend to strike a lightning rod before it will strike something below the lightning rod, because it's an easier path to get to Earth. So your friend will be ever so slightly better route for the lightning to go than you are, because she's got this big metal rod down her back. But you're actually, compared to air, you're a very, very good path, so it's going to be trivial difference. If she actually had a big, sharp, pointy thing sticking out the top of her head, that might make more of the effect, but I very much doubt she has.
Because lightning conductors don't actually protect a building by attracting lightning. They actually deflect the lightning around the building, don't they, by effectively creating a sort of shield, a coronal discharge of electrons flowing around the building, and that provides a lower resistance route to ground for the lightning.
Yeah, they do 2 things. One of them is that they are a good path. If the lightning is going to hit the building, they'll hit the lightning rods, and therefore the building doesn't catch fire. And the second one is that they can essentially discharge the lightning in that general area. They discharge it, so it's less likely to strike in that area. But the radio thing, I think, is quite likely, because essentially she does have a great big piece of metal in her back. Big pieces of metal act like aerials and can reflect radio waves and do all sorts of strange things to it, in the same way as you can to a slightly lesser extent. So yes, I'm sure she does affect radio.
You better not come around my house, because I have a terrible job picking up anything where I live. She may improve it even. Oh, well, OK, in that case, I'll plug her in. Thank you, Dave.
Well, it's now time for this week's Planet Earth, and Richard Hollingham has been to Edinburgh Zoo to speak to Edinburgh University researcher Laura Kelly, who studies bowerbirds. Now, these are natives of Australia and Papua New Guinea, and they look a bit like a cross between a crow and a pigeon, and they build impressive bowers to attract their mates. But it turns out they're also highly impressive mimics.
The species that I work on, spotted bowerbirds, they build a long U-shaped bower. It's about 50 centimetres long, and they construct that out of a stick base, and then they put grass pieces along the side of the bower, and then in the middle of this bower they put pieces of green glass and clear glass, and then they have a big pile of snail shells at either end.
And it's not just that, they also mimic other birds and in fact other animals, other things in the world.
They mimic up to 14 bird species that we've got recordings of. They definitely mimic a wide variety of sounds and, as you mentioned, environmental sounds, including people.
Well, let's talk about that mimicry, because that's what you've been looking at. I think we can hear some of these. First of all, this is what a bowerbird would normally sound like. So almost a hiss-like sound.
Yeah, it's a very harsh, broadband kind of hissing sounds, and all the bowerbirds produce quite a similar kind of harsh sound. And this is the vocalisation that they use when they're kind of communicating with each other.
But they can also produce the sounds of other birds. This is a kite, for instance. This is a real kite. But this one is a bowerbird mimicking a kite. It's really difficult to tell the difference.
Yeah, it's very easy to be fooled by them, actually. So when we were looking at mimicry, we only classified it as mimicry if we could actually see the bird producing the sound, because it is, as you say, very, very accurate.
But it's not just other birds that they can mimic.
They also mimic environmental sounds, so there's reports of them mimicking the sound of dripping water and twanging fence wire, wings flapping, and also people. I've got a recording of a bowerbird, or 2 bowerbirds in fact, that mimic a lady calling for her cat, which is called Bonnie.
That's amazing. How long did it take for the bowerbirds to get that?
Well, the lady has owned the cat for less than a year, so they've picked it up in under a year. The lady also calls for the cat at least once a day, so they've only probably had 1 or 2 exposures to it daily, and then they've picked it up in under a year, so they can obviously learn them moderately quickly.
And how common is this for bowerbirds?
As far as we know, all bowerbird species mimic. To what extent they all mimic, we're not entirely sure. Because many of them are in remote locations, we don't always know as much about them as we would like to.
What do you think's going on here?
Well, it's not entirely clear to us why this particular species mimics. So in some of the bowerbird species, they mimic as part of their sexual display. So as well as building their impressive bowers, they also produce mimicry of other species to attract a lady. With this particular species that I work on, the spotted bowerbird, it could be that they mimic aggressive and predatory species as a way of deterring either potential predators or rival bowerbirds. The other thing that it could be is that the sounds that the males mimic are all quite simple and they're very common and loud in their general sound environment. So it could just be they're almost learning these sounds by mistake because they're simple and very loud.
So they could just be going on anyway, and the fact is there's no disadvantage to them mimicking rather than there being an evolutionary advantage.
Exactly, yeah.
Laura Kelly from the University of Edinburgh talking to Planet Earth podcast presenter Richard Hollingham. You can download the latest Planet Earth podcast and find links to its host website, Planet Earth Online, at thenakedscientist.com/Planet Earth.
Thanks, Sarah. You're listening to The Naked Scientists. Chris, Sarah and Dave are answering all of your science questions. And Andrew is in Norwich. He's on the line now. Hello, Andrew.
Good evening. I was just wondering if you know what the mechanism is that controls your CSF pressure.
Cerebrospinal fluid.
Yeah.
Yeah.
And if there's any way of lowering it.
OK. Well, let's explain for people who are not in the loop what this is. So your brain and spinal cord sit inside your skull and the cavity that runs down inside your spinal column, and they're invested in some layers called the meninges, which wrap up the brain and spinal cord, and inside those layers is a fluid called cerebrospinal fluid, and the brain bobs around in that fluid, and it effectively acts as a cushion to support the tissue because the nerves in the brain are very delicate and they need that additional cushioning support. The cerebrospinal fluid is actually made right inside the brain. You have a network of blood vessels called the choroid plexus, and those blood vessels work rather like a coffee filter. So the blood goes through them, and the walls are slightly leaky, and liquid, but not cells, comes out of the blood and goes inside some holes in the brain called ventricles, and it flows out of those ventricles and then out into the space around the brain. And then right at the top of your head, between the two hemispheres, is a structure called the falx cerebri, F-A-L-X, falx. And in there is a very large blood vessel called the sagittal sinus. And the dura, which is one of the layers of the meninges, makes that special blood vessel, and it's perforated in various places by these structures called arachnoid granulations. And these are little pouchings that are mushroom-shaped of the additional layer around the brain, the arachnoid layer around the brain, and the CSF goes up into those little mushroom-shaped bodies and is reabsorbed into the bloodstream via that route. So blood comes out of the middle of the brain, goes around the brain, and then is reabsorbed into this big blood vessel that runs from front to back in the middle of your head. And the reason that the pressure can go up is if those arachnoid granulations get blocked, or if that big blood vessel, the sagittal sinus, gets blocked, and sometimes if too much CSF is produced as well for whatever reason. You can lower the pressure by treating the underlying condition, whatever has caused the obstruction, or by reducing the formation of the cerebrospinal fluid in the first place. And one way to do that is to give a drug called a carbonic anhydrase inhibitor. I think one of those is a drug called acetazolamide, and this will reduce the rate at which CSF is being formed, and therefore the pressure, the CSF pressure, drops a little bit. So that's the reason. But a very interesting question. Thank you very much. Sarah, here's one for you. It's from Joe Barber, who's emailed to say, do large eyes see better than small ones? And he's referring to things like a very big eye that you might find in a squid versus, say, a very small eye you might see in a kestrel.
Well, I think the idea behind, if you have a bigger eye, well, you want to get as much light onto your retina as you can so you can get a more detailed picture of the outside world. So you often see large eyes in nocturnal animals that rely on sight, things like eyes and bush babies, or fish, or indeed cephalopods like giant squid in the deep sea where it's constantly dark. So either they can be predators and they need to see their prey, or they need to be determining distances to jump between branches, that sort of thing. It's kind of not necessarily just a question of how big the eye is, but you also need to think about what you're doing with it. So if you have a large pupil, you'll need to have a larger eye, so a deeper eye, in order to get the focus depth right. Because if you have a big aperture and you just let the light into the eye, then you need to make sure that it's deep enough in order for you to get the focal length, otherwise you'll have a big blurry picture. So you still need to have the focusing power of a lens going on there. So if you can't focus the light, it's quite useless. Also, things with bigger eyes that need to see more often have a larger optic lobe in their brain because they need more processing power and that sort of thing. Now, this is just the case for simple eyes here. We're not talking about compound eyes, which are the sort of things that invertebrates like insects and crustaceans have. Although I do know that mantis shrimps have the most complex eyes of any invertebrate, and they have 16 different types of light receptors, whereas we only have 4.
Lucky them, I say. Thank you, Sarah. Dave, here's a quick one for you. I think, well, in fact, maybe we can share this one. I love it. So Natalie and Ray Etherton have said on Facebook, with all of the dust falling on our planet and the occasional rock, like the one from 65 million years ago, has this increased the gravity of our planet since it was first formed? And if so, by how much? So we're going to need your calculator again, Dave. I know that the consensus of opinion for the amount of mass descending onto Earth from space annually is now about 40,000 tonnes, or the weight of a modest aircraft carrier, every single year. So the Earth is 4,500 million years old, and we'll assume that it's been roughly the same ever since, because otherwise we're going to get tied up into all kinds of knots. But so what is 4,500 million times 40,000?
Comes out roughly about 160 million billion tonnes.
It's quite a lot, isn't it?
It's an awful lot compared to us, and it's quite a lot compared to anything we might come across. However, the Earth itself weighs about 6 million trillion tonnes. So it's going to be about a 10 millionth of the mass of the Earth.
So in the grand scheme of things, it's trivial.
Yes, if the rate of stuff falling down had been constant all the way through the Earth's life. However, that obviously isn't the case, because the Earth was formed by stuff sort of crashing into it and all coagulating and forming a big lump from lots and lots of meteorite type things. So the assumptions we've made are completely wrong, and in fact the whole of the Earth's mass has come from meteorites
and stuff accreting. You're right, because if you take it to its logical conclusion, the Earth came from particles falling together. So you could say, well, 100% of the gravity of the Earth is because of stuff raining on to the Earth, effectively.
But not for a long time.
Exactly. Thank you very much, Dave. OK, here's another one. Richard says, why is frost bad for freezers, Dave? Why should the frost be bad? I thought snow and frost is a good insulator, so why doesn't it keep the freezer cold for longer? Why do people say it's bad?
The problem is because it's a good insulator. The way a freezer works, you have a load of pipes at the back, you compress a gas in the pump, that makes it hot, it loses the heat out of the back of the fridge or freezer. It then pipes this compressed room temperature gas into the freezer. It then expands, evaporates, gets cold, and so the coldest bits of the fridge are where this expanded gas is flowing through. The problem is that wants to be able to get the heat from the fridge to be able to absorb onto it. If you've got a great big layer of ice, that's going to insulate the cooling part of the fridge from your fridge, so the fridge is going to be warmer, which means that the actual freezer's got to work harder to keep it cold, which means it gets even colder, which means you get more ice, and it all builds up and it goes horribly wrong until the fridge just conks out mostly.
And you have a big bill. Thanks, Dave.
I've got a question here from David Worley94 on Twitter, and he says, how was the first organic molecule made?
I presume he means in space, with the evolution of the universe, or at least let's assume that's what he means, because that's kind of interesting. Well, this was a question that scientists struggled with for a very long time, including quite a famous scientist, Stanley Miller, who did the really famous Miller experiments in the 1950s, 60s, 70s. And one of the things that he was intrigued by is the possibility that the complex life on Earth all arose from building blocks that were built up to make complex chemicals in situ here on the Earth in the early days of the planet's history. And he did a very exciting experiment, and Ben Valsler and I went to the University of California, San Diego, to meet Jeff Bader, who worked with Stanley Miller and has all of his equipment and, in fact, all of the results of his experiments, which he found in a laboratory at Stanley Miller's laboratory when he cleared it out when Stanley Miller died. And that experiment consisted of taking a glass flask, putting in a source of hydrogen and carbon and a source of nitrogen and some water, and mixing up those gases in the absence of oxygen in this flask and heating it up to a very high temperature so it boiled off, and then passing the vapours past a spark created between two electrodes. And he ran this thing for about a week or so, and what started off as a clear fluid in the bottom of the flask soon became chocolatey brown. And when he analysed the products, he found at least 20 different chemicals. And when Jeff Bader reanalysed all of the chemicals that were in there about 20 years later using a mass spectrometer and very modern techniques, he found there were hundreds of complex organic chemicals in this mixture. So in terms of the early Earth and probably the early universe, what this experiment suggests is that you can make quite complicated, quite big molecules, including the building blocks of life, amino acids, by recreating these conditions and having a source of energy, ionizing radiation perhaps, and all those key molecules, and you can then get some exciting chemistry happening, which will produce a range of different things. So I think basically it's not that difficult, is what this is saying.
Yeah, since then people have found these complicated organic molecules all over the universe. They've found them in meteorites, they've found evidence for them in just big molecular clouds floating out in space. There's huge clouds which are mostly made up of ethanol out there, which would be an alcoholic's paradise. And so basically all you need is some of the right kind of elements, some carbon, some oxygen, some nitrogen and some hydrogen, and something about the right temperature, and some, as Chris was saying, a source of energy, some ultraviolet light kicking around, not too much, but about the right amount. And so the first time in the universe history when that's going to have been common is after there's been some big supernovae, because supernovae make the heavier elements. Before then it was mostly high. There might have been a few created just from the Big Bang, but the numbers would be absolutely minute. So you just need some supernovae to have gone bang, and then stars starting up from their remnants. So a couple of billion years after the Big Bang, and I'm sure there were lots and lots of organic molecules kicking about.
And of course, I suppose by organic here we don't mean sort of like, the organic vegetables that you find in your supermarket that haven't been grown with pesticides. We just mean molecules that have carbon in them.
Yes, and obviously the simplest organic molecule is something like methane with just some carbon and some hydrogen in it.
OK, I've got a question for you here, Chris, and it's from Ash Dunn on Twitter, and they would like to know what would happen to the bubbles in a fizzy drink at zero gravity.
Yeah, well, that's a really interesting point. What would happen if you took your Coke, I suppose you could say Coke Zero, into zero gravity? It is zero that Coke make, I think, isn't it? I hope it is. The answer is that when we're on Earth and you crack into a can of drink, it fizzes up because the bubbles know what's up and what's down, because there is a density gradient in the fluid. The bubbles are less dense than the liquid is because they take up a lot more space than they actually weigh, and as a result they're pushed towards the top of the fluid. They float. Now, if you're in space, there is no up and down because there is no gradient like that in the same way. So if you actually do produce a fizzy drink or some froth in space, what happens is the bubbles just sit there, interestingly. And scientists have done this from NASA. They actually took some Alka-Seltzers to the International Space Station and dissolved them in water inside a plastic bag so they could see what the bubbles did. And you get a range of bubbles of different sizes. And what happens is that you get a small bubble formed, and because it's easier for a small bubble to get to be a bigger bubble, then all the small ones join in and they tend to coalesce, and you get a range of bubbles, but they're all fairly large, but they remain static in three-dimensional space. So you just have this bag of fluid with bubbles perched all over the place in it, not glued to the side, but inside in the body of the fluid. So the bubbles basically won't float like they do on Earth.
So I guess it's very like what happens if you shake it up and you let it expand very, very quickly. You just get a big foam.
Yeah, you do, and it looks quite nice. You can look on the internet, actually, and see pictures of froth in space, and you'll see all these really nice frothy rafts, if you like. It's quite striking. An interesting experiment. I'm glad that NASA are spending lots of money doing important things like fizzy drink research in space. No, I'm just kidding. It certainly had me glued, anyway. Now, it's that time of the show where we have to get hands-on and interactive for a bit of kitchen science. Dave?
OK, it's a lovely little kitchen science experiment for you. What you need is 2 bendy straws. And a pair of scissors. I want you to take one of those bendy straws and chop it off so it's symmetrical about the bendy bit. So the 2 sides are about the same length either side of the joint. So if you cut that off there. And now what I want you to do is basically poke the other straw you've got, the short end of the other straw, the end closer to the bendy bit, inside one of the ends of your short one. The problem is it won't go straight in, so you're going to have to crush one end, sort of fold it in half long ways for about a centimetre, and then jam it inside the other one.
Oh, I see. So we're inserting the short end of the long, surviving, uncut bendy straw into one end of the one we've just trimmed.
That's exactly right. So you've now got one extra long straw with two bends in it. I now want you to put the long end in your mouth.
Okay.
And then you're both looking very fetching there.
That's really silly.
And then move your hand down to the first bendy bit, stretch it out, and then bend that down 90 degrees.
Mm-hmm.
Good 90-degree bend on that.
Yeah.
And then work your way down to the other bendy bit, and then bend that to the left by 90 degrees.
Okay.
So you've now got a sort of doubly kinked straw.
Uh-huh.
I now want you to just sort of support it with one hand and put it a long way into your mouth, and then blow hard through it.
Oh, yay!
Mine shot off.
Oh, it spins.
It's
spinning.
It's spinning beautifully. Yeah, this is a lovely example of Newton's laws. Essentially, you're blowing air through the straw, so the straw is pushing air out sideways. So the air is being pushed out sideways, which means the air is going to push the straw in the opposite direction. Essentially, you've got a jet which pushes the straw round and round and round and round, and you have a jet-powered rotor. They've actually built helicopters which work on this principle. It means you don't need a tail rotor because there's no net torque on the helicopter.
I'm assuming they didn't use bendy straws to do that.
I think they probably use something rather more sophisticated in aerospace, much more expensive.
It's pretty good that I found, actually, if you put your two palms together like you're saying a prayer with the straw running between them, just lightly support it, you can actually get it to whiz around quite fast.
There's a bit of a knack to it. Now
like that, Sarah. Yeah.
Now, that's a really difficult question. What happens when you suck?
Oh, God.
What's the obvious thing that's going to happen when you suck?
It's going to go the other way.
Try it.
It'll go the other way because it's sucking it in, maybe?
Harder.
Sarah's turning red.
Nothing happens.
Breathing in too much. No, nothing. Was I doing it wrong, or is nothing supposed to happen?
Nothing happens. No, this is a fundamental thing about sucking, because what you're doing when you suck is reduce the pressure at the end of the straw. That sucks in air from every direction. So the air coming in has no momentum, so it can't. So it's because it's all average. It's all coming from different directions. There's no overall momentum, so there's no momentum to transfer to the straw. So the equal opposite reaction. There's no reaction to opposite, so there's no force on the straw, so it doesn't move.
So stay static. So this we put into the introduction. We said this is why you get a rocket taking off. It's pretty much the same principle, isn't it?
Yeah, a rocket works by throwing gases downwards, and the rocket gets pushed upwards. And this is, of course, the reason why you couldn't suck an aeroplane along. There'd be just no force.
Although Brunel did, of course, have his atmospheric railway, where he had a long tube with a low pressure in it and a piston in that tube, and he was trying to get the atmosphere to push the train along by effectively doing work against that very low pressure behind the piston.
That's right. If you've got a piston there, you can suck a piston along and it all works fine. But in free air, you couldn't suck an aeroplane along.
It's probably a good thing. Dave, thank you very much. You need a very long straw, if nothing else, wouldn't you? Thank you, Dave. And you can see Dave doing that on our website, and there's a full write-up of the science behind it too at thenakedscientist.com/kitchen science. And if you click on making a rotor, you'll see a picture of Dave looking rather red in the face as he's trying to blow through it, but it does look good, worth the look. It is The Naked Scientist. Chris Smith, Dave Ansell and Sarah Caster-Perry. We're answering your science questions for you, as well as doing funny things with straws. Did you have a go? Send us in a picture or text us and tell us what it was like in your kitchen trying to do that experiment. Sarah, why don't you have a go at telling us, because Justin Smith would like to know, can a lobster drown?
Well, the simple answer is no. Lobsters have evolved to live in water. They exchange gases through their gills, and they will actually die if they are out of water for too long, but they will actually survive for a small amount of time. Their close relatives, crabs, can actually survive out of water for a bit longer. And although if you take a fish out of water, it will die because they will essentially suffocate. When they're in water, their gills extract oxygen from the water, but when you take them out, the surface tension of the water makes the gills collapse, so they can't function, they can't get the oxygen out of the water. Now, some fish do actually have adaptations for air breathing, like lungfish, if they live in places like rivers that periodically dry up, so they need to be able to deal with that. Now, the reason that crabs and to a certain extent lobsters, but not as much as crabs, can actually survive in air for a time, is that they hold their gills in cavities on the undersides of their bodies. Now, they don't actually breathe air. They're still using their gills, but they've found a way of keeping them supported and moist, which is the most important thing. And there's actually a species of crab called a coconut crab, and they've evolved something called a branchiostegal lung, which is kind of a spongy tissue, which is like a cross between gills and lungs, which still need to be kept moistened, but they will actually exchange gas with the air. So lobsters do also have gills in chambers, but they still require water. So they will survive in air as long as the gills are kept wet. They also have something called a gill bailer, which has the best name. It's called a scaphognathite, which helps to keep water moving across the gills. So they will suffocate if they're in air, but they will not drown in water.
Terrific, thank you. Dave.
Right, I've got a question here for you, Chris, from George Pope. He was, by the sounds of things, playing American football once, got tackled incredibly hard, and when he came round again, all he could see was stars. So why do you see stars when you hit your head?
Yeah, it's a cartoon, isn't it, when you see the cartoon character get socked around the head and then you see the stars going around the head. It's probably because you get two things happening. One is that when you slam your head down against the ground or some hard object very quickly, you get what's called a contre-coup injury, because the brain bounces around inside your skull, because although it's cushioned by the cerebrospinal fluid, if it's travelling sufficiently fast, there will still be a degree of shock in the brain. And if that impacts on the visual areas, then it triggers a bit of pressure to be applied to the visual nerves, or the nerves that present consciousness, the fact you're seeing something, and as a result they get active. And if they're active, they're going to make you think you're seeing things that are not there, but they're not going to be built images, because that involves whole assemblages of nerve cells. It'll just be random cells here and there, and as a result you see these little spots of light, which we interpret as stars, because that looks like the most sensible thing to say that they are. So it's probably a trauma thing. The other time you occasionally see stars is when you stand up too quick in the bath, and this is a blood pressure hypoperfusion thing, because when you're hot in the bath, all of your blood vessels dilate out to get as much blood as close to the skin surface as possible to cool you down. So when you stand up, you've got lots of blood in your peripheries, very little is actually returning to the heart, and so there's a drop in blood pressure just transiently, and that impacts on the retina, which has a very high metabolic rate. And if you interrupt the blood flow just for a fraction of a second to the retina, all of the nerve receptors in the eye that turn light waves into brain waves just start firing off all kinds of visual signals, and you see those starbursts, and that's probably the reason why. Sarah?
Is that kind of also a little bit like if you rub your eyes too hard and you start seeing little lights popping all over because the pressure in your eye is activating the photoreceptors?
Absolutely, that's another entoptic phenomenon. If you press on the eye, you're deforming and distorting the retina, applying pressure to the photoreceptors. This could do two things. One, stimulate them in exactly the same way, like you say. The other is it could just move them a fraction away from the blood for a fraction of a moment, and that is enough to make them a little tiny bit oxygen deprived, and so they start also firing off these funny signals. So yes, you're on the right lines. Right, we're fast running out of time, so I just have to read this one from John in Wollaston. He says, "Hi Naked Scientist, great programme," and he wants to ask us about compact fluorescent bulbs. So what we'll do, John, is we'll try and squeeze that in right at the end. But before then, here is this week's Question of the Week with Diana O'Carroll.
This week, how the brain reads what it feels.
Hi, I am Frederik Kremers. Because I am visually impaired, I read braille instead of normal text. So I was wondering, does the mind process text in a different way when reading braille? Thanks for taking my question. Bye.
So with text and braille sending messages via different senses, how might the brain interpret them?
Okay, I'm Dan Goldrake, and I'm an associate professor in the Department of Psychology, Neuroscience, and Behavior at McMaster University in Ontario, Canada. To answer your question, we need to understand how the brain processes both touch and language. And with respect to touch, when we move our fingertip over objects such as braille characters, receptors under the skin produce electrical impulses that race at about 50 meters per second through the nervous system and up towards the brain. And this pattern of electrical impulses, a sort of neural Morse code, activates a part of the brain's parietal lobe, roughly halfway between the forehead and the back of the head. This tactile area of the parietal lobe helps to decode the neural impulses in order to infer the shapes of the objects that touch the skin. Now, interestingly, in blind people, particularly those blind from birth, touch activates not only this tactile area of the parietal lobe, but also a part of the occipital lobe in the very back of the head that is normally reserved for vision. So a blind person reading braille will experience activation of both the tactile area of the brain and the normally visual area of the brain. This unusually extensive brain activation may underlie the heightened sense of touch in blind people, However, in reading Braille, the brain must not only perceive the shapes of the characters, but once it has done so, it must understand those shapes as language. And this linguistic understanding is probably not occurring in the brain areas I've just mentioned, but rather in the brain's language areas, such as the area of the temporal lobe above the ear called Wernicke's area. So a blind person reading Braille is probably using the same language areas of the brain as a sighted person would while reading print, and as you are right now as you understand the words that I'm speaking. So with respect to the question, does the mind process text in a different way when reading Braille, the answer is both yes and no. Blind people reading Braille do show an unusually extensive pattern of brain activation, but once the brain perceives the tactile shapes, the subsequently activated brain language areas that work to understand the Braille words are probably the same as those used to understand printed or spoken words.
In blind people, the sense of touch is interpreted by a part of the brain more usually involved in vision, as well as the brain areas typically used for touch. But both text and Braille are probably deciphered by the language area of the brain. And next week, how are black holes possible if light is massless?
Hi, I am Ayush Panwar, and my question is, how can light be deflected? Because according to Newtonian gravity, gravity is a property of mass. Then how can light, which is considered massless, be deflected due to gravity?
How is it that light bends due to gravity when it is supposed to be without mass? Answers on our forum at thenakedscientists.com/forum, or write to us. The email address is chris@thenakedscientists.com.
Diana O'Carroll. So, Dave, can you help John in Wollaston? I want to know, he says, how is the energy used in the new efficient energy bulbs better than the old fluorescent bulbs, given, say, 100 watts of light?
Well, the efficacy of the light bulbs, which is a measure of how much light, visible light, they produce per watt, for a old-fashioned fluorescent is somewhere between 50 and 67 lumens per watt, whereas a compact fluorescent is between 60 and 72. So similar, but possibly slightly better because they're newer with the compact fluorescents.
And more people are using them, which is on population scale important. Dave, thank you very much, and brilliantly done in about 20 seconds. Well, that's it for this week. Next week we're back looking into the matter of antimatter. We'll be discussing where all the antimatter went after the Big Bang, and also finding out why and how researchers have been able to trap and study the antimatter equivalent of hydrogen. Don't forget, you can catch up with anything we've covered on the show on our website at nakedscientists.com, and the news stories are there too. Thank you very much to our production team, Ben Vousler, Tom Simpkins, Mira Semthalingam, Louise Ogden and Diana O'Carroll. Send your emails to chris@thenakedscientists.com. Have a great week and see you next time.
The Naked Scientists comes to you from Cambridge University and is supported by the Wellcome Trust, the EPSRC, the Natural Environment Research Council and UK FAST. For more information, look us up online at thenakedscientists.com.